Section 6.3, Logistic Equations, Introduction. I am on page 16F in your lecture manual. So you'll want to go to page 16F for this lesson. So a logistic curve is one that starts out growing slowly, then grows rapidly, then continues to grow, but slows down its rate of growth. If we were in class, what we would do is we would do a little experiment with a random number generator. Let's say I have 35 people, and I want to look at the spread of an infectious disease. And so I'm going to list my days. And let's say that on day 0, one person is infected. Somebody comes to school that's sick. So after the first day, when one day has passed, there's now 2 people sick. And again, I would be doing this with random number generator on my calculator to model it. After the second day, let's say there's 4 people. After the third day, let's say there's 8. After the fourth day, let's say there's 13, and we continue in this pattern until all 35 people in the class have gotten the disease. If I were to graph these points, 0, 1, 2, 4, my function would look like this. Don't write it down yet. I'll give you a moment to do it in a minute. See how it starts slow and then grows faster, and then still is growing but slows down. You can see the nice little inflection point hiding around in here somewhere. But now I actually want to look at my rate of my spread. Now we know that that's just the change in population over the change in time. So the first day that I can do, look at rate of spread is the first day that's passed. So 2 minus 1 over 1 minus 0, that is 1. What about the next one? 4 minus 2 over 2 minus 1. That rate of growth is 2 people per day. On the third day, 8 minus 4 over 3 minus 2. 4 people per day. On the fourth day, after the fourth day, 13 minus 8 over 4 minus 3. 5 people per day is my rate. And following that procedure, I would get this. Now, look at the graph. Where does it look like we are increasing the most rapidly? Where would my tangent line have the steepest slope? Well, it appears to be about right there, right? If I follow the slope of a tangent line along the curve, my curve has the steepest slope around here. Well, notice my steepest slope is happening around day 5. So this is day 0, 1, 2, 3, 4, 5. Well, notice if I were to take the derivative of this, notice that this is always increasing, so its derivative would be above the x-axis, and my steepest slope on my function is about right here. So on the derivative, that would be the highest y value. And my derivative is going to look like this. Okay, I'm going to pause the video and let you take a moment to write this down nicely in your lecture manual. Right, what does the shape of this curve represent? That represents the number of people infected. What does the rate of spread represent? The rate of the spread of the disease. It represents the slopes of the number of people infected, the slopes on my number of people infected curve. So if I look a little more closely at my derivative graph, what we have is the rate of change of my population with respect to time. And here's my population. Now, I only had 35 people in my class, so my total amount of people that could get it was 35. Notice that my highest rate of spread happens halfway in my population, when half the population has it. Oh, so if I go up here Look at that, 19. That's a little more than half, but we're modeling a situation, so that's pretty close. Okay? When is this disease not spreading? When no people have it or when all people have it? When is it spreading the fastest? Well, in my data, by day 5, about half the people have it. Now, our differential equation for a logistic model is, I love this, the rate of change is proportional to the population that has it and the population that doesn't. So you will see this like this often. So you should remember when we did the first part of section 6.3 with our growth and decay function, that eventually we got y equals c e to the kt. We did this by separating the variables in a differential equation. Okay? And we use that equation in various growth and decay problems. Now we're going to derive an equation to be used in spread of diseases, spread of rumors, training time estimator, certain types of population growth, sales of a new product, impact of advertising. All of these are applications of a logistic model. But what we were not able to do earlier is we were not able to do work with these types of functions because we needed partial fractions to integrate. So it is almost a guarantee that you're going to see this in some form on the BC exam. It is a big topic, so it will be helpful for you to know once you have your equation in differential form how to get it into the solution form. So the rate at which an infected population increases is proportional to the infected population and the uninfected population. The rate of growth is proportional to the people that have it and times the people that don't. Okay? And we want P as a function of time. So the first thing that we're going to do is take this equation and separate our variables. Remember that L is a constant. It is not a variable. And integrating requires the use of partial fractions. Remember what we just learned is I have P times L minus P. So I want to write this as A over P plus B over L minus P and use our methods that we learned in section 8.5 to actually find what A and B should be. So now I know that this fraction is going to become these two fractions. And using the method of partial fractions, we get A to be 1 over L and B to also be 1 over L. So the integral of 1 over L over P plus 1 over L minus P with respect to P is equal to the integral of K dt. Now, let us remember, L is a constant. Therefore, 1 over L can be brought out in front of our integral. And we know how to integrate this. Okay, the integral of 1 over P dP, we know what that is, minus the integral of 1 over L minus P dP. We are integrating with respect to P. We can see that this is U prime over U. We can see that if I had a numerator that had -1 in it, I would have U prime over U, so I'm going to take care of that. And here's my equation. Now we're ready to anti-differentiate everything. Factoring out the 1 over L, this anti-differentiates to natural log of P. My population is never negative, so we don't need bars here. This is U prime over U, anti-differentiates into L and U. Again, the total population that can have it minus the population that currently have it will never be negative. I don't need absolute value bars. Equals, now this side is what you should know from previous. K is a constant times T plus my unknown constant C that's going to be for everything. And using our log rules, we know that this becomes this. Now, remember that before we do log is exponent, we need the log part completely isolated, which means this L needs to get multiplied by both sides. That is going to give us this. And now log is exponent. This is my exponent on E, which equals P over L minus P. Now, we know what this looks like. e to the LKT plus LC1 really means we know e to the LC1 is going to be called C. So what I have here is P over L minus P equals e to the LKT times e to the LC1, or P over L minus P equals C e to the LKT. That's a lot of variables, but let's remember L is not a variable. Well, what I want to do is reciprocate this. And we're going to let B be 1 over C. And let's remember that e to the LKT in the denominator is e to the negative LKT. So now this becomes L minus P over P equals BE to the negative LKT, or KLT. So now this over here can become two fractions. We can simplify the P over P. Now let's remember, what are we solving for? We're solving for P. So I would add 1, multiply by P, and remember we're solving for P. So that means we're going to divide by this. So it looks terrible, but it's not too terrible. Now we're going to introduce another variable. A is going to equal negative K times L. So now I get P equals L over 1 plus B e to the AT. Could you have left it like this? Sure. And you're going to see several different versions. But the big idea is rate of growth is proportional to population present times the population not present. And that becomes, the population is L, which is a limiting factor, over 1 plus B e to the AT. Now we're on page 16E. Riverdale High School has a population of 1,000. On day 0, 20 students start a rumor. A day later, 50 students have heard the rumor. All right, my limiting factor, or my total population, is 1,000. On day 0, 20 students have the rumor. One day later, 50 have it. What is a model for the population of students P who have heard the rumor on day 1? So I need P as a function of T. How many students have heard the rumor by day 8? So I want P of 8. When is the rumor spreading the fastest? So I want to know, when is it spreading fastest? When half the population has it. So I want to know at what time is my population 500. In other words, 500 people know. Now, as I told you a minute ago, you're going to see several versions of that equation. Here's another one. P is L over B e to the AT plus 1. See, same thing we just did. And as I told you, we can also write this as, this coefficient could be called A, could be called anything. And my A right here, which was negative K times L, could also just become negative KLT. So there's a lot of ways to represent it. All right, let's look at what we know. We know that my limiting factor is 1,000, and I have this at day equals 0, there are 20. Now, what can I find from here? Well, I get 1,000 over 1 plus A. This is going to be e to the 0. Now we can solve this easily. Multiply by 1 plus A, divide by 20. So 1 plus A is 50, so A is 49. Cool, I have that number. And now I want to use the second part of my problem, which was, after 1 day, 50 people know it. I have my A, I need to find my K. So after 1 day, 50 people know it. And we're going to do proper algebra that you should know how to do. I'm going to multiply by the denominator, divide by 50. 1,000 over 50 is 20. And we're just going to unpack this until I get e to the power alone. Subtracting 1, dividing by 49, it looks terrible. Take the natural log of both sides. We are going to do this in the calculator and store that value. Remember that K is equal to this divided by negative 1,000. So here's finally my population as a function of time. There is our answer to part A. B, how many students have heard it? 5 to 8. All I've got to do is substitute 8 into that and use my stored value. And we want to answer this correctly. We don't have 0.57 of a person. So we would say 975 students or 976 students have heard the rumor by the 8th day. This is how you would answer it on a free response. You don't stop with this. You don't stop with this. You state the whole thing. Part C, when is the rumor spreading the fastest? We know that generally the rumor is spreading the fastest when half of the population has it. So I'm going to take my population function and set it equal to 500 and do the necessary algebra to isolate my e to this power so I can find my t. Okay. Multiplying by the denominator, dividing by 500, subtracting 1, divide by 49, and take the natural log of both sides. I kind of did that in one step. Solve for t is approximately 4.108. So the rumor is spreading the fastest on the 4th day. Here is to write this down. Pause the video. Your TP for this section, 6.3.2 Intro, go to Lecture Manual, page 16H, and work number 1. See you next time.